In this session, let us do some kind of intricate analysis in open delta connection. And before that, whatever we analyzed in our previous session, let us revise in the name of a problem. Okay, so if I think of delta connection is this, okay, and this is the source and this is the load, and this delta is connected to a load. For example, each single phase transformer is having a capacity of 250 kVA. Okay, if I have delta connection, what is the rated capacity? Rated capacity is going to be, in delta connection, rated capacity is going to be 3 into 250 is going to be 750 kVA. For example, if load demand is 750 kVA, meaning that each and every transformer is fully loaded, okay, rated. And if I think of open delta, because this is very important, that are you sitting at the transformer side or are you sitting at the load side? We should be able to differentiate, otherwise problem will come. Okay, anyway, we are going to take other old gate or old IS questions, then automatically you will understand. Anyway, see here, in open delta connection, how much will be the capacity? 57.7% of three-phase capacity or 86.6% of installed capacity. Okay, now the moment I remove this, then how much is the installed capacity? Single phase is 250, so 250 plus 250 500, or 250 plus 250 500, 500 into 0.866. okay, so this is going to be installed capacity 500 into 86.6% of it. Or I can write it from three phase point of view. If I have three phases, it would be 750. 57.7% of 750, anything is fine. So 750 into 57.7% or 0.57 is going to be 433 kVA. Okay, now if I have this rated capacity, if I sit here, if this is the rated capacity of this is maximum, I can operate up to 433 kVA. Now one may ask, see here, this installed capacity is 250, so combined should be, like a layman if we think, combined should be 500 kVA, no, 250, because under open delta condition, if it is operating at rated current, with rated voltage, okay, with rated voltage, rated current, meaning that insulation is fully stressed for rated voltage, and my copper volume is completely utilized by sending or by carrying rated currents. So rated current, rated voltage, in the sense it is going to give rated kVA, now rated kVA 250 plus rated kVA 250 should be 500, but it will not be 500, it will be 433 kVA. Now let us think of from load side. Okay, so from load side, if I maintain same 750 kVA, okay, because load is not in our control. If load is demanding more, my machine will be overloaded. If it is maintaining same 750, means I am sitting in the load side. If it is maintaining same 750 kVA, definitely these transformers will be overloaded. By how much percentage it will be overloaded? Simple. Okay, means my load is operating at 750 kVA and my rated capacity is 433 kVA. So in open delta, if it is maintaining 750 kVA at the load, each transformer will be overloaded by 750 by 433. That's it. So 750 by 433, which will be default 1.732. right? So this is going to be 1.732, or it is going to be overloaded by 73.2%. okay, now let us think of, if this particular load demand is reduced by 25%, okay, then means each transformer will be overloaded by, okay, so load is reduced by 25%, meaning that remaining load connected is going to be 75%. okay, now if I think of, now the load demand is 0.75 into 750. In this condition, it will be overloaded by 0.75 into 750 by 433. 0.75 into 750 by 433 you will get, or else I can write it as a Means if load demand is 750 kV, it will be overloaded by 73.2%, but it is reduced by 25%, meaning that extra overloading will be reduced. So it is going to be 1.732 into remaining is 0.75. 75% of load is maintained. So it is going to be overloaded by 1.732 into 0.75, 1.299, meaning that each transformer will be overloaded by 29.9%. So each transformer will be overloaded by 29.9%. Now, like a layman, if you think, means my installed capacity is 250 plus 252 two transformers. So installed capacity is 500 kVA. Now, like a layman, it means internally what is going to happen, you don't know. Okay, so like a layman, if you apply 500 kVA, okay, installed capacity is 250 plus 250, so we applied this, so it will be overloaded by 500 by 433. Okay, so each transformer will be overloaded by 15.47%. So overloaded by 15.47%. That's it. Okay, so point here is very simple. Are you sitting at the load side? Are you sitting at the load side? Are you sitting at the transformer side? You have to think. For example, let me think of another color, pink. Okay, for example, it is not 750 kVA now. It is just 250 kVA. Or maybe 200 kVA, because otherwise you may see same numbers. Go 250. For example, if load is not 750 kVA, it will be 200 kVA. If it is 200 kVA, how much load each transformer will bear? Okay, can I say 200 is the output, such that 100 will give this, 100 will give this? No. It should be more than that. Because if I think of 500 kVA here, okay, or okay, let us think of 433 kVA here. Okay, if I think of 433 kVA here, this transformer is delivering 250 kVA, this transformer is delivering 250 kVA. Okay, or from formula point of view, if you see, S of open delta is going to be how much? Is going to be root 3 V phase, I phase, or V rated, and if you think of, in order to calculate rated capacity is going to be higher. Now, can I say I rated has to be considered? No, it should be, means some other than load, it is going to be phase current. Okay, such that I phase current, it is not full load, it is not rated. I phase current into rated voltage into root 3 times is going to be S of open delta. So V rated into phase current is going to be S of open delta by root 3. Okay, if I think of S of open delta is going to be how much? 200 by root 3 is going to be V rated I phase. V rated I phase is going to be, that is going to be the kVA. So 200 by 1.732. So each transformer is going to deliver 115.47 kVA. Each transformer is going to deliver 115.47, such that 115.47 here, 115.47 here, output is going to be 200. It will not be 115.47 plus 115.47. Why it is happening, we are going to see now. Okay, if output requirement is 433 kVA, okay, that is the maximum rated capacity of this particular transformer without having the transformer connection or combination, without overloading any of the transformer. So if I think of 433.33 kVA, if it is operating at rated, is it giving 433 by 2? No. 433 by root 3, such that it is operating at 250 kVA. It is operating at 250 kVA. 250 plus 250 is going to be, output is going to be 433 kVA. Okay. Now, in order to analyze what is happening inside, or why 100 plus 100 cannot be 200, it will be less than 200 by root 3 and all. Okay, so why this is happening, in order to know that, we should understand phasor diagram. Okay, and in the phasor diagram, the main point here is, if you think of open delta, okay, if you think of open delta, many of the maybe other guys will focus on, see here this is phase current, no, because this is not there. If I have delta connection, if this is phase current, if this is phase current, this is going to be root 3 times phase current. Okay, but if I think of here, I phase is going to be IL line current, and I phase is going to be IL line current, but nobody show you here, because if this is IP, this is IP, how can this be IP? Means we should know, a bit of kind of intricate analysis has to be done. Okay, means once if you see this, you need not see any time. Okay, anyway, let me connect a load, and at starting let me connect delta connection. Okay, basically though it's a bit small time consuming, okay, but still in order to understand open delta, first of all delta should be understood. Okay, now let us think of this is connected with star connected load. Okay, if it is connected with star connected load, and let me think of, see here, one thing here we have to, already in networks multiple times I said, if I write Vxy, what does it mean? With respect to y, how much is the potential of x? With respect to y, how much is the potential of x? For example, Vxy, if this is x, this is y. Okay, with respect to y, with respect to second letter, how much is Vx? This is going to be Vxy. Because polarities are very much important in representing voltage, and direction is very much important in representing current. Now let us think of current. Okay, if I think of current, if I write I maybe PQ, if I have P here, maybe some element, if I have Q here, P to Q direction of current is IPQ. Okay, so P to Q, how the current direction is there, so that is going to PQ. Now one more thing here, because everybody is saying here IA, here IB, here IC, it will not be like that, because it is going to be in phase, inside the transformer or inside the winding. We are supposed to write, and we are supposed to show, and we are supposed to represent the terminology properly. Now if I think of generator and load, okay, so if I think of this as X, this as Y. Now in the generator, current will be from Y to X. Current will be from minus to plus at least. If I think of same X here, because equipotential points, if I think of same Y here, current will be X to Y direction, because plus here, minus here, plus to minus current will flow. So here direction of current is IXY. Here direction of current is IYX. Okay. Now if I write voltages means if I think of plus here, minus here, because plus minus, so this voltage is going to V of X with respect to Y. Okay, so in the load Vxy, Ixy will be there, but in the source current is going to be IYX, and voltage is going to be V of X with respect to Y. Of course, in networks multiple times we have seen. Okay, this is the in the generator, current will go from minus to plus. In the load, current will go from plus to minus. Okay, now let us think of this as A, this as B, this as C, such that this is going to be A, this is going to be B, this is going to be C, and this is going to be neutral. Okay, just it take maybe 10 minutes or some time, but we have to understand this. Okay, now if I think of plus minus, okay, so with respect to B, A voltage, so with respect to B, A voltage, BAB, minus plus, such that AB plus BC plus CA will be 0, because polarities has to maintain. And here with respect to A, C voltage, and here with respect to C, B voltage, BBC, such that VAB plus VBC plus VCA equal to 0. Now let us try to show the current directions. Current will go from minus to plus or plus to minus. That will be decided by whether it is means delivering power or absorbing power. Okay, means secondary of transformer, is it a kind of generator or load? Secondary of transformer is a kind of generator because it is supposed to deliver power. Okay, so current direction will be in this direction, minus to plus. How much is that current direction? I, B to A, B to A. Okay, and current direction here is going to be I, A to C. Current direction here is going to be I, C to B, such that VBC, ICB will come. VAB, IBA will come because it is source. If it is load side, VAB, IAB, VBC, IBC, VCA, ICA, something like that will come. Okay. Anyway, let us try to draw the phase diagram for this. Phase diagram for this. Now, if I think of this voltage as VA, this voltage is VC, ABC phase sequence as usual. This is B. Okay. Now, let me draw. Let me a bit reduce this. Okay, let me draw VA or VAN. Okay, let me write VAN. Okay, and here VB, here VC, VCN. Okay, now if you think of current, if I have resistive load, current should be in line with voltage. Okay, then current is going to be IA to N, because current is going to be IA to N, because plus to minus current will go. Okay, so if I write VAN, it is going to be IAN, that's it, because it is load. Okay, and here this current is IB, and here this current is IC, or IAN, IBN, ICN. Okay, now let us convert this into, means from load side I have taken reference. Let us come to source side. Now what is VAB? VA minus VB. Okay, because with respect to B, how much is A voltage? So VAB is going to be VA minus VB, such that with respect to B, A voltage, with respect to B, A voltage. Okay, now see here, VA is here minus VB. Okay, VB minus VB, such that VA minus VB is going to be VAB. Source, no, capital VAB. Okay, and the angle between, in three-phase systems also we have seen, right? So angle between line voltage to phase voltage will be 30. In ABC phase sequence, line voltage lead. In ACB phase sequence, line voltage lag, and all we have seen that. Okay, now VAB, VBC, VB here, VC here, minus VC. VB minus VC is going to be VBC. Okay, now let me think of VC minus VA. This is VC minus VA, VCA. Let me remove unnecessary things. Yes, yes, yes. Okay, that angle is going to be 30 degrees. Now let us see here only the whatever we have to learn in delta connection, here it will come. Okay, see here, maybe let me think of red only. Here between what they say phase voltage and phase current, load is resistive, that's why IA is here. Now if you see IBA minus IAC should be IA, no? IAN or IA, that's what we started, right? So this current is going to be IBA minus IAC. Okay, so IA or IAN is going to be IBA minus IAC. Now where is IBA should be, or where is IAC should be? For example, if I think of my VAB is here and IBA is here. IBA is here, for example, just like that, and IAC, ICA is VCA is here, IAC is here, just like that, stay. Okay, IBA minus IAC is IA, IBA minus IAC is going to be IA. Problem solved. Okay, such that means focus. See here, of course, remaining phase also same thing will come, because everything is symmetric here. It is not like open delta. In open delta, we have to analyze for all the phases. Okay, now if I think of here, means you have to remember that, means if in the star connection VA IA in line, to each other means phase voltage, phase current are in line. Line voltage, line currents are, sorry, see here phase voltage, phase current, here load is resistive, and inside voltage and current also will be in line in single phase. Okay, so for example, here rated current is flowing, here rated current is flowing, here root 3 times rated current, because IA value is more, IBA minus IAC. Okay, if load is resistive in nature or operating at unity power factor, my transformer also, because this is the transformer, right? So transformer inside current is in line with voltage, such that IBA, IAC, end is going to be root 3 times phase current will come. So such that this IA is going to be root 3 times magnitude, IBA or IAC, anything is fine, or phase current, let me write phase current. Okay, so here rated current is flowing, here rated current is flowing, here root 3 times rated current of transformer will flow, such that means this is going to be phase voltage is going to be line voltage here, not at the load. Okay, so here this voltage and this current are in line. Now if you want to add this voltage, this current, plus this voltage, this current, plus this voltage, this current, everything will be in line, everything will be in line, such that directly it can be added. Okay, for example, see here, for example, see blue, black, blue. If VA, IA means if IA is lagging behind VA by small angle, means complete system is going to be lagging. Okay, such that VAB, IBA also will be lagging by the same. Okay, focus. See here I have taken resistive load, VA, IA, load side, VA, IA are in line. Okay, yeah, VA, IA are in line, meaning that VAB, IBA means inside transformer voltage, single phase transformer voltage, single phase transformer current are in line. If IA is delayed, okay, or lagged by some angle pi, automatically complete system is going to be lagged, such that with respect to this voltage, current is going to be lagging behind by the same angle. So that's why we are going to get, for example, if I think of each is 250 kVA, means each transformer is 250 kVA. Okay, net resultant is going to be 250 into 3 is going to be 750 kVA, because phase angle difference will not come. Now let us see the open delta connection. In open delta connection, as I said, most of the members don't focus on A. Now let us focus on A. Okay, so this is open delta. My focus is phase displacements. Only secondary side, because primary side will be anyway there and all, we need not bother about it. Okay, now let us see here, A as usual, B, C, and this is A, this is B, this is C. Okay, if I think of VAB, okay, so plus minus VA value with respect to B, minus plus, okay, and again here minus plus. Same concepts. If three sources are connected in a loop, such that each source, okay, each source, if you apply KVL, net value is 0. So voltage source across one source, voltage across one source is independent of presence of that source, we have seen. Okay, now see here, minus plus. So minus plus is going to be, this is going to be C value with respect to A. Anyway, here current will not flow, so in KVA shared to the load means this particular winding will not participate in any kind of currents. And source current is going to be in this direction, minus to plus, so this is going to be I, B, A, B to A, and source current is going to minus to plus, so this is going to be I, A to C. And my load currents are, let me think of it, load currents are, this is IA or IAN, and this current is IBN, and this current is ICN. Now if we analyze this, you will get the clarity. Why? Because this phase current is this line current, this phase current is this line current, but two phases are there, but this magnitude of current, this magnitude of current, this magnitude of current, how can it be same? Many guys have this doubt, and as I covered up in my previous session, okay, we can cover up like it should be balanced load, so this current should be same. Okay, covering up the things. But anyway, let us see now how the current distribution is going to happen. How, like, even though it is operating at 250 net capacity at rated conditions can be 433 kVA only. Let us see now. Okay, now as usual, the same, everything is going to be same. Let us try to draw the phasor diagram. Okay, so let me reduce the size a bit. Hope it is visible. Okay, now let us think of here VA, VB, VC. Okay, so from load to source, let me develop the phasor diagram. This is VA, this is VB, this is VC, such that phase sequence is ABC, you know. Okay, now VB. Okay, let me think of resistive only. Currents are in line. Okay, because from load to source I'm trying to develop. So currents are, this is IAN, this is IBN, this is ICN. Right, now let us try to develop currents. Right, okay, see here, what is IB? IB is nothing but minus of IBA. Or what is IBA is nothing but minus of IB. So if IB is here, minus of IB is nothing but IBA. Okay, now let me think of IAC is nothing but IC only, no? IAC is nothing but IC only. Where is IC? Is nothing but IAC. AC. Okay, now let me try to calculate IA. What is IA? IA is going to be entering current IBA minus leaving current IAC. Is going to be leaving current here. Let us see whether the magnitudes are becoming same or not, or whether the 120 degrees displacement is being maintained or not in open delta connection. Okay, frankly speaking, because of only this, people exactly don't catch the open delta connection. Now anyway, let us see. IA equal to IBA minus IAC. IBA minus IAC. IBA minus IAC. Minus IAC is going to be this plus this. Okay, so let me change actually to IA here. Okay, so just a minute. So this is going to be IA here. This is going to be VA here. You got it, right? Now let us see IA, IB, IC values. Okay, see IB equal to IBA. Okay, so IB equal to IBA and IC equal to IAC, such that if this length is 1 ampere, for example, if this particular phasor length, this is 1 per unit or 1 ampere, for example, 1 ampere, 1 ampere, 1 ampere. Now means from here to here, how much is the angle? 120. Okay, and from here to here, how much is the angle? 120. So from here to here, how much is the angle? 60. Or from here to here, how much is the angle? 60. How much is the angle from here to here? Is 60. So 1 per unit, because means if load is balanced, 1 per unit, 1 per unit, 1 per unit, IA 1 per unit, IB 1 per unit, IC 1 per unit. Okay, now this is 1 per unit, this is going to be 1 per unit, this is 1 per unit, this is going to be 1 per unit. So net is going to be 1 per unit cos 60 into 2. 1 per unit cos 60 plus 1 per unit cos 60 is going to be 2 into 1 per unit into cos 60 is going to be 1 by 2. 2 will get cancelled. So this also is going to be 1 per unit. Meaning that if this current magnitude, this current magnitude is same, compulsorily this current magnitude will be same. From the phasor diagram we can identify. Okay. Now anyway, let us go to the required conclusions. What are those required conclusions? See here, if I want to write VAB means how much is VAB? VA minus VB. Okay, see here, this is VA minus VB is nothing but this is VAB Okay, VAB, see here, VAB is the voltage here. Let me calculate other voltage also. VCA, VC minus VA. See here, VC minus VA. VC minus VA. Minus VA is going to be VC or AC? CA. VCA. Okay, now let us think of line voltages or whatever it may be in transformer. In transformer, this particular phase voltage, I am sitting at transformer now. So how much is the voltage here, rated voltage? How much is the current? Let us see. Okay, so in this particular transformer, how much is the voltage, how much is the current, and what is the angle between them, if you see, provided if it is unity power factor. If it is unity power factor. See here, which color? Let me think of pink. Okay, see here, VAB is the voltage here. VAB is the voltage here, which is appearing in the transformer, one phase of the transformer, and another voltage is VCA is another voltage. Okay, now two windings, two voltages are there. What about the two currents? IBA is one current. Where is IBA? Okay, VAB, IBA. Okay, so VAB is here, IBA is here. IBA is here. So that is the voltage current character, voltage current displacements in this particular winding. How much is this? With respect to voltage, it is leading by 30 degrees. Okay, if I think of this is rated voltage and this is rated current. Okay, if I think of this is rated voltage and this is rated current, then how much is the kVA supplied by this to the transformer? Basically, some rated current is flowing through this. Rated current is flowing through this. At the same time, rated voltages are there. But here, means this is going to be rated current, this is going to be rated voltage. So it's going to be rated voltage, rated current at an angle 30 degrees lead. Okay, now let us see another transformer winding. Another transformer winding is VCA IAC. Current is VCA, voltage is IAC. So VCA is here and IAC equal to IC. So it is here. It is here. Okay, here what is happening? If this is rated voltage and if this is rated current, I am sitting at the transformer. Okay, if transformer is operating with rated current, it is going to give you rated kVA, but between voltage and current is lagging behind voltage by 30 degrees. So means kVA supplied by this to load is going to be at rated conditions at an angle, it is lagging minus 30. Okay, so with respect to voltage across the transformer, current is leading by 30 degrees. With respect to voltage across the transformer, current is lagging at 30 degrees. But load, if you see, VIA are in line. Getting my point, right? So if you consider this, so this is going to be VR IR cos 30 plus J VR IR sin 30. Anyway, signs will get cancelled, you know, plus VR IR cos 30 minus J VR IR sin 30. This and this will get cancelled. So how much, even if you maintain rated voltage, rated current, cos 30 is coming. So this cos 30 plus that cos 30 is going to be 2 VR IR cos 30. Cos 30 sin 60 root 3 by 2, 2 will get cancelled, such that root 3 VR IR. Okay, so if each transformer is operating at rated voltage, if each transformer is operating at rated current, how much is the net capacity coming out? Maximum, that too this is rated. Okay, maximum is going to be root 3 V rated I rated. That's what we got now previously also at unity power factor. So this is going to be rated voltage is there, rated current is there, at unity power factor. This is the situation. Okay, now you can try at your end. See here, I don't know how far you can connect. See here, with respect to this voltage, what is this voltage? Load voltage. With respect to this voltage, if current is lagging behind. Okay, so if IA lag behind, IB will lag behind, IC will lag behind, such that, see here, focused. Okay, if IB is lagging behind, my IBA is nothing but minus, IB is nothing but minus IB, no? IB minus IB is going to be IBA. So this IBA is going to twist in this direction. Okay, so see, balanced load, right? If it is balanced load, the angle between VAIA should be equal to VBIB should be equal to VCIC from the load. Okay, the moment I have, rather than resistance, let me have resistance and inductance. Then what will happen? Let us see. See here, if IA is lagging behind, if IB is lagging behind with respect to VB, if IB is lagging behind, means minus IB is nothing but IBA. So for example, if IB is here, means with respect to VB, this is IB, lagging behind by pi. Then what will happen? Means the moment it is coming here, it will come here IBA. Meaning that this is going to be 30, means this shift is pi. So this shift is pi. So this is going to be 30 minus pi. Okay. For example, see here, IC is nothing but IAC, I think. IC is nothing but IAC. IC is nothing but IAC. IC is nothing but IAC. So see here, the moment IC with respect to VC, if IC is lagging behind by pi, so it's going to be 30 plus pi. Lagging angle will be, means actually many guys are not focusing here. Lagging angle will be 30 plus pi. Leading angle will be 30 minus pi. Okay. If 30 minus pi is positive, it is going to be leading. If 30 minus pi is negative, it is going to be lagging again. Okay. Now let us see here. Total is going to be at rated conditions. At rated conditions, if power factor of the load varies, is going to be at an angle, okay, 30 plus pi is going to be lagging. You have to remember this. 30 plus pi is going to be lagging, plus V rated, I rated at an angle 30 minus pi. 30 minus pi is going to be leading. If pi is less than 30, it will be leading. If pi is more than 30, it is going to become lagging. Okay. And anyway, this will be all the time lagging only. So you can keep minus here. If you keep minus here, of course, we know that VI complex conjugate, we know. Okay. But still, if I think of this as, because VR, forget about it. If you want to calculate IR at an angle minus 30 plus pi, you need not remember anything. Okay. 30 plus pi is going to be lagging, 30 minus pi is going to be leading. If you get positive value here. Okay. Now let us consider the same old problem, whatever we discussed. Okay. 250 kVA each. So each is going to be 250 kVA. Each is going to be 250 kVA. And net output can be 433 kVA, right? Okay, if each single phase transformer is having the capacity of 250 kVA in open delta connection, my net output kVA should be reduced to 433. It will not be 250 plus 250, or it cannot be under rated conditions. Under rated conditions, I am sitting at the transformer. Under rated conditions, if power factor varies, how the situation is going to be, because immediately after this, if we can analyze this, we know, we don't forget. Okay. So kVA is final. kVA requirement is final. But here, let me vary power factor. Because one volt question came, gate question, and most of the members solution is wrong. Okay. Anyway, see here, 433 kVA means if rated load, means this is the load that can be supplied is 433 kVA. So let me add 433 kVA, let me vary the power factor. So this is going to be, for example, 433 kVA only output at unity power factor. Now if I think of S1, first transformer is going to be unity power factor, no? So 433 by root 3. Okay, each transformer is going to be total capacity. Okay, let me do this. So open delta equal to root 3 V phase, I phase, or V rated, I rated in this case. V rated, I rated. Okay, let me write V rated, I rated only. V rated, I rated. Or how much is V rated, I rated? V rated, I rated is going to be single phase capacity. So V rated, I rated is going to be S of open delta by root 3. S of open delta means rated, I am assuming 433 by root 3. Okay, is going to be, how much it will be? 433 by 1.732. So 250. Oh, sorry, that is rated condition only. I'm sorry. It is 250 only. Okay, means each and every individual transformer is fully loaded. Okay, so in this condition, at unity power factor condition, so first one is going to be total, S total is going to be S1 250 at an angle, means it is leading, plus 250 at an angle minus 30, meaning that 250 into cos 30 plus j sin 30 plus 250 into cos 30 minus j sin 30. This is going to be the output. Okay, so S total is going to be 250 plus 250 cos 30 is going to be 433 kilowatt, because unity power factor, no? So this is going to be 250 cos 30 plus 250 cos 30 is going to be 433 kilowatt. It's fine. Okay, but if you see each and every individual transformer, see here 250 cos 30 will be there, 250 sin 30 is 0.5, so 250, so here, okay, let me cos 30 root 3 by 2, no? Root 3 by 2 into 250, 216.5. So S1 first transformer is going to be 216.5 plus J reactive power of sin 30.5, 125. So this plus this is going to be 250 only. Okay, 250 kVA, meaning that out of 250 kVA, 216.5 kilowatt of power it is giving to output, and 125 kVA reactive power it is supplying. But output side it is UPF. Now who is going to absorb that? Another transformer is going to absorb. Okay, and S2 is going to be again 216.5 minus J 125. It is going to be as usual 250 only. Okay, what does it mean? See here, my first transformer is delivering 216.5, second transformer is delivering 216.5, such that this plus this is going to be 433 kilowatt. But first transformer is supplying reactive power, second transformer is absorbing reactive power. That's why net output kVA is reduced. So it is operating at 250, but active power output requirement is active power only. But inside one transformer voltage current settings, if you see, one transformer current is leading, another transformer current is lagging. Okay, such that one transformer is supplying reactive power, another transformer is absorbing. Internally this is happening. Okay, now let us think of maybe at power factor at 30 degrees PF lag. Load is having 30 degrees PF lag. Okay, so how much will be the load? Is going to be 433 kVA at an angle 30. Okay, now how much is S1? S1 is going to be 433 by root 3, which is nothing but 250, because each transformer is operating at full load, no? 250 at an angle. Lagging if I consider 30 plus pi. Okay, so 30 plus 30 is going to be 60. If you think of S2 is going to be 30 minus pi leading. So this is going to be 0. 30 minus pi equal to 30 degrees only, no? So in this case, what's happening here? So this is going to be, okay, 250 cos 60 sin 30 is going to be 125. Okay, and S1 means 30 plus pi. This is lagging, and this is anyway unity power factor. Stay focused. Okay, 125, and it is lagging in the sense S1 is supplying reactive power, and about supply reactive power, absorb reactive power, already synchronous is over, right? So after synchronous, if you watch, means lagging power factor source deliver reactive power, lagging power factor load absorb reactive power, such kind of things. So it is going to deliver 216.5 kVA. Okay, it is delivering reactive power. What about this? It is delivering only active power. That active power is 250 kilowatt with the unity power factor, such that 250 plus 125. Okay, so if you divide this, let me divide because answer should be same, no? 430 at an angle 375 is the active power plus J 216.5 is the reactive power. Okay, so this much active power requirement is there at the output. Active power transformers only has to supply. Okay, so see here, active power should be supplied, focus, and reactive power also should be supplied. See here, this transformer is supplying exact reactive power for this, and this transformer is only supplying active power only. Active power of 250 plus 125 is 375. What does it mean? See here, S1 is delivering active power also, reactive power also, but S2 is delivering only active power. So internal, one transformer is delivering reactive power, another transformer is absorbing reactive power. Such kind of stuff will not be there. Only at unity power factor it can be there. Now if you think of 30 degrees power factor angle, load. Okay, so this load is having load voltage to load current per phase difference is 30 degrees. Then inside the transformer, this is the situation such that active power, it means my conclusion is in between these two transformers there will be no reactive power supply and reactive power absorption. Whatever may be the reactive power supply here, directly it will go to here. Okay, let me think of 60 degrees. Okay, so if I think of, means V rated, I rated only, but at 60 degrees power factor lag. Okay, then S1 is going to be 250 V rated, I rated at an angle 60 degrees or 60 plus 30, and S2 is going to be 250 into at an angle 30 minus pi, so 30 minus 60. Now you got minus 30 in the sense it is going to operate at lagging. It is going to operate at lagging by ZPF. Okay, so this is going to be, see here, 250 at an angle cos 90 plus J sin 90, cos 90 0. So it is going to supply only reactive power 250 kVAR. Cos 90 is 0, no? So it is supplying only reactive power. Now if you think of here, okay, means 30 minus 60 means 30 plus pi, 30 minus pi. 30 minus pi, if it is positive, that transformer is going to operate at leading. 30 minus pi, if it is negative, it will be lagging. So this is going to be 250 at an angle cos 30 it is supplying, so plus J sin 30. Okay, so cos 30 sin 60 root 3 by 2, so 250 into 0.866, it is supplying of power. Don't think of minus will come here, think of reactive power, is it supplying or not? So this transformer is supplying only reactive power, I kept plus. So this transformer also has to supply reactive power because source lagging power factor has to supply reactive power. These many times we discussed in synchronous. Okay, now plus sin 30 is 0.5, J 125. Okay, so this is 125 reactive power plus 250 is the reactive power. So total 375 is the reactive power supply. And here, maybe previously we might have 250 into 0.866, 216.5. So 216.5 is the active power and no active power here. So individually if I add up, okay, so this is going to be 216.5 is the active power plus J 125 plus 250 is going to be 375 is the reactive power supply. Okay, 30 minus pi, if it is positive, it will operate at leading. 30 minus pi, if it is negative, it will operate at lagging, which will supply reactive power. Okay, now if you think of at 60 degrees 430 kVA at an angle 60 will come here only. Okay, meaning that in this case also, okay, what is happening here, in this case means inside transformer to transformer, reactive power is not flowing. Whatever the each transformer, it is directly supplying to load. Each transformer directly supplying to load. So we have taken unity power factor, load, 30 degrees lag, load, 60 degrees lag, load. Out of these three conditions means indirectly means among inside the transformers some reactive power supply, some reactive power absorption is there only at unity power factor, okay, and depending upon the equations, okay. But at 30 degrees, whatever may be the reactive power is being supplied by each transformer directly going to output, whatever may be the transformer which is delivering active power combinedly is going to output, okay. And if you think of 60 degrees also, means inside transformer to transformer reactive power, it means one transformer is supplying, another transformer is absorbing. Such condition we considered only at unity power factor, okay. That will be decided by whether 30 degrees is more or 30 degrees is less, okay, with respect to 30 degrees and power factor angle, which will be decided, okay.